and script. Okay, so today it's about causal inference, and similar to what I've been doing over the last couple of days, I would like to know from a show of hands, how many of you have heard of causal inference, have used it before? Nobody has heard of, okay, one. Okay, couple of people, good. Okay, a couple of people have heard about it, great. By a couple, I mean several couples. So causal inference is a technique that if you study economics or epidemiology, they might use different names, but it's basically a way for you to estimate the causal effects. So you probably hear of causality, correlation is now causality, or something along those lines. And so these are techniques to try to get at the cause. What are the factors that actually cause outcomes to change rather than some correlation? I would argue that many of the things that we see in science of science are associations, correlations, but recently, and I think because we're moving perhaps more into policy, and it's totally my opinion, we are using other techniques that from econometrics and in causal inference to do that. So I'll try to give a very brief introduction to the concepts and then do like a demo with code. That is also very simple, but the general idea, I think it will be captured by these demos. All right. Okay, so the motivation, I kind of already gave it, that you want to find the causes rather than the correlations. I'm going to introduce a framework that was introduced 40 years ago or more about how to think about this statistically or operationalize causal inference. And then I will talk about directed acyclical graphs, which is kind of another camp of causal inference that uses graphs to represent or to kind of make some assumptions about the causal relationships between factors in their data set. And then we're going to talk about the backdoor criteria, which is a way of thinking about what are the factors that you need to control so you can make causal claims. And then we'll do an example, an estimation. So, of course, the dream that we all have is to do causal inference based on observations, on data that we have. Let's say we have OpenAlex or MAG, and that's data that was already captured. So we want to make causal inferences without doing randomization or a randomized control trial, right? Which is kind of the gold standard for estimating causal effects. And that's what this criteria means. We want to, based on observation data, what are the things that we need to control to make these claims? Okay, but let's see. So motivations here, like a couple of examples of questions that you might want to ask. And this is general. It doesn't need, it's not even related to science of science. It's related to examples of a system that you want to study. It could be a system of people or a system that just works on its own. So the important thing is that even if you have machine learning or a very sophisticated statistical model that predicts with 100% accuracy something, that doesn't mean that there is a causal relationship. So even let's say if we're predicting citations or something like that based on some factors, even if we can predict with 100% accuracy the citations 10 years from now with some factors, that doesn't mean that there is a causal relationship between those factors and that outcome. Okay, So now, why do we want causal estimations? Well, because we want to know, let's say, if something will work. Does a change in the system improves people's outcomes or some outcome? So let's say if we're predicting citations and we use a factor related to the institution of the person to predict the citation. Well, does that mean if I move the person to another institution, let's say that has higher ranking or lower ranking, depending on the relationship we found, will that change the outcome, or it's just a prediction? Okay, so like why? Another question could be like, why did it work? What led to a change in an outcome? So we see a change in citations. What was the thing that caused it? So that's the same thing but reversed. So another example is, what changes to a systems are likely to improve outcomes for people? Very similar to the first question. How does the system interact with human behavior? What is the effect of systems recommendations on people activity? Now, so these examples come from a package that, I think it's a software package that Microsoft introduced called DoWhy, and it has many techniques for causal inference, and these examples come from systems that Microsoft run. So they are interested in knowing, the causal effects. They're interested in knowing changes, and all the companies, of course, are interested in this. Facebook, Google, like does showing an ad in this way, will that change the behavior of people when they click an ad or something? Will that improve the click through of that ad? So you can make that prediction 100% accuracy, but that doesn't mean that there is a causal relationship. There might be something else. Now, how is that possible? So I'm going to look at a very, very simple example that shows that with code. Okay, so before that, I want to say that most of the things that I'm showing here, I borrow from this book, Causal Inference, the mixtape, and it's an online book in the sense that you can buy it, but you can read it online, and you have the codes, R code, and Python code to run the examples as well. So it's like a very nice way of looking at the theory and the code at the same time. Okay, so this is an example of this. So suppose that we have a data set of all the panels that are here below, right? Or this row here. So if you look at this and you see the x-axis and y-axis, you might think, well, in all of them there is a correlation, right? So we have the Pearson correlation coefficient here. For all of them, it's about 50%. It's highly significant, so the p-value is much smaller than 1%. So you might be tempted to say, okay, so this means that X is causing Y. So if I make a change, let's say if I have a subject, let's assume this is a person, a subject with this value of X, if I increase it, then the value of Y of that subject will increase. The same here, right? So you might be tempted to make those inferences. However, if you look at the way that we generated these graphs, the story is a little different. Okay, so let's look at this one first. So this is a function from Python, but it doesn't need to be Python. It's just some function that generates random numbers. Okay, so imagine these are the random values, the random independent variables of our unit of study. Okay, so we're going to sample from that, and this then is going to be inputted here when we produce a Y. Okay, so Y is now going to be X plus 1 plus some noise. Okay, so if you see here, if I change X, okay, so if I set the value of X, I will have a change in the value of Y. right? So if I put x equal 10, let's say, well, I guess x equal 1, that will influence the value of y. I think that's clear, right? Any value that I put here in x, if let's say I've set it in the code, I would change the value of y. Okay, so by having the knowledge of how the data is being generated with this code, we can say, oh, there is a causal relationship between x and y. X is causally producing y directly. And we can see it in the equation. If you look at the data, there is no way to tell. They all look the same. Like, look at this example here. We first generate y, and then we generate x. So this is the opposite in the sense that y is generating x. And the way to think about that is, okay, let's fix the value of y to, again, like 4. That's going to change the value of x. If I change that, if you have had like a slider there in y, it will change the value of x. So in this case, it's the opposite. Here, in the green case, y is causally generating x. Now, this is the most common problem that we have in our lives. We see a relationship, but then and we try to capture everything that we can. Let's say we capture x and y, but we miss a variable that is explaining both things. So if we set, let's say, the value of x, that won't affect y. If we set the value of y, that won't affect x. So what's going on here? Well, there is a confounding factor, what's called in causal inference. There is this factor called z that is affecting both. But there is no relationship between x and y. And this is usually what happens when you say, okay, let's say, I'm going to use this example from economics. If someone has high levels of education, well, I guess if someone is, okay, I mean, this is not realistic, but let's say someone has a high level of education, they usually earn more, but there might be an intrinsic factor that affects both. So they have, let's say, more social connections, or they have more money as children. They had more money as children. So that is affecting the chances of getting an education, and that's also affecting the chances of making more money, because through the connections that they made when they were young, they were able to make, find better jobs, but maybe there is no connection between education and how much you make. That's not really true, but this is just an example. But we have all these kinds of confounds in data and in science of science. So any questions about this? I find this very illuminating. It's just such a simple example of what's the problem with just using data to try to make causal inference claims. Okay. So we're going to try to think about how to do this more mathematically. And the way that we're going to do it is through two ways, basically. One is called the potential outcome framework. From that, we'll borrow the notation, then we'll use something called a DAG and backdoor criteria to actually do the estimation of causal effects. And the seminal paper was this paper from Ruben. I believe he's at Harvard now, probably retiring soon, perhaps. And he introduced this idea. Now, the idea that of potential outcomes and the statistical description of this could be controversial philosophically for the reasons that we'll see now. Okay, so potential outcomes is defined as this. So the notation, it could be a little confusing at the beginning, but basically we have a y. Just think about the y letter, and that represents an outcome. So let's say it could be the number of citations, the earnings of someone, whatever we're trying to predict, whatever we're interested in understanding. What are the things that affect that? Okay, so this could usually it's just a number, a real number. The subscript I represents the units of analysis. So there could be a paper, scientist, a patient, and the superscript represents whether the person received the treatment or not. And here we're going to be talking about just binary treatments. So it could be this person did this paper, was this paper published by a famous scientist, let's say. Okay, how that affects the citations. So that will be the treatment, just 0 or 1. Okay, so 1 means he received the treatment, he's a famous scientist or some other thing that we're interested in understanding how it affects the outcomes. Or superscript, yeah, treatment is whatever we're interested in understanding. So it could be, let's say how we improve the what affects this again, how it affects the citations of a paper. You want to think about, okay, what is the factor that we need to change so that we change the citations of someone. So let's say the factor is, okay, we need to move into a new institution. That will be the treatment is 1, moving into a new institution, and 0 will be not moving to a new institution, just staying in the current institution. And that's my personal case. Okay, so this is simplifies things. We have a variable that is binary and want to see how it affects the outcome. Of course, the most intuitive example is when you think about medical treatments, right? So if you have cancer, or if you have some disease and you want to cure, someone proposes a treatment. That's what this means. Either you receive the treatment, or 0, you presumably receive a placebo. So what is the difference between the outcomes of the disease? Okay, but here's the problem with causal inference. So this is the fundamental problem of causal inference. Okay, the fundamental problem is that we want to understand the difference between this variable and this variable. Okay, so for a given unit, we have a patient I. We want to understand what is the difference in potential outcome between giving the treatment to that person and not giving the treatment to that person. The problem, of course, is that it is the same unit. Okay, so if it's the same unit, we cannot see both outcomes. When we give the treatment to someone, we cannot go back in time and not give the treatment to the same unit. So unless it is a multiverse and you can travel to wormholes, that's not possible. So that's the fundamental problem of causal inference. We cannot observe the potential outcomes of both treatment and control. So we can only observe one state of the world. Each unit has only one state of the world, and that's the problem. Okay, so we define another variable that's called yi and y0, and that doesn't have the unit. Because we just that's just the outcome of the potential the actual outcome of the observation. And yi is going to be defined by whether we give the treatment or not to the person. So it doesn't. We cannot really try both options of giving the treatment and not giving the treatment for the same unit. So D will be a variable that defines the treatment. This is the variable that we, let's say in our case, we're interested in understanding how it affects the outcome. So in the case of the citation problem, how does the changing something changing someone from institution, how does that affect the citations of someone? Okay, so that will be D, moving someone across. Okay, so D is the assignment. How do we assign the unit when we're doing the experiment? But as we'll see later, this could be also observational data, not necessarily an experiment. So the outcome of someone, the potential outcome the observable outcome, which is y subscript I, it's going to be completely defined by this equation. And this is might be a little confusing, but basically, if someone receives the treatment, the I will be 1. So with the outcome, the observable outcome will be y subscript yi 1. If we don't give the treatment to someone, the outcome will be yi 0. Okay, so this is what this is stating here. So by just the simple fact of giving the treatment to someone, we're only get to observe one of the potential outcomes. So we are interested in understanding this, right? We're interested in understanding the delta of giving the treatment to someone versus not giving the treatment to someone. Is it possible to have more than one treatment? It is. It is possible, and we can generalize this. But all the applications, all these, this is relatively easily generalizable. And I quote that because you have to look at the books that do that. But yes, it is possible. Okay, so this is what we're interested in. We're interested in the treatment effect for a person. But with this we cannot observe because we cannot see both outcomes for the same person. So what we do instead, we think about the average treatment effect across the population. Okay, so we take the average treatment effect, and they have all these abbreviations. We want the expected value of the treatment effect, and by the properties of expectation, that can be separated. So that could be the expectation of one quantity minus the expectation of the other quantity. Okay, but this is impossible again because we don't have we cannot observe both things at the same time. Now there are other things that we can other factors that we're interested in. So we might be interested in something like this. Given that we give the treatment to someone, what is the effect? What is the average treatment of the treated? So that's conditional on that given the treatment to someone, what is the expected value? Okay. Now notice here, this is called a counterfactual. Okay, because this is given that we give the treatment to someone, what would have been the outcome if we had not given the treatment, if we had not given the treatment to that person? It's a little mouthful. What would have happened if we had not given the treatment to someone? Okay, so we cannot observe that. So ATT might likely differ from ATE. So the average treatment of the treated might differ from the average treatment of the average treatment effect because people react to treatment. So people who receive the COVID trial vaccines were in general more scientifically oriented, careful. So that changed. So we are selecting a different population. And we can do the opposite. What is the treatment effect on the untreated? But none of these quantities can be observed, so we need to make assumptions. So here's an example data that's where we see everything. Okay, this is from the book. We see both what happens if we give the treatment to someone, what happens if we don't give the treatment to someone, and these are the indices. So this is, again, this is impossible. So we have patient 1. This is the outcome that happened if we give the treatment to someone. This is the outcome that happened if we don't give the treatment. So we can compute the delta directly. And the average treatment of the treated, you can look at this. You just look at this. The average treatment of the treated is, let's see. We just compute this difference. Oh, this is, let's see, a little too big. Okay, good. So we can have like some paradoxes in the sense that sometimes if we just are naive and estimate from the observations what are the outcomes, that might not give us a sense of really what's happening within units. So this happens usually when you have differences across the population and difference within the units. So you have, let's say, someone within itself would respond better to a treatment, but if you look across the entire population, it seems that the effect is not there. So this is really hard to get rid of because again, you cannot observe these quantities. So you have to be very careful in this case. Okay, so what's going on here? Okay, how can we think about this? Now, what you observe, so in your data, you won't have both outcomes. Okay, again, I'm repeating the same thing over and over again, but we will have that. So what we will have, however, is just, we can like very naively, and this is just, again, one variable affecting another, or we assume that affects another, and we have just the differences in outcomes. So D here would be whether we move someone to a new institution, and Y will be the citations in 10 years or something like that. Okay, so we can take that data, we can think about that question and go to OpenAlex and take a look at that. And we can take just the simple difference in outcomes of the observations that we have, right? So this is just a simple average. This NT is the number of people that are treated, people that move into an institution. NC is the number of people that are not treated, that didn't move to an institution. Y is the citation in 10 years of those people. And we just take the differences in those averages. Okay, so and this is from the book, so it goes through the derivation of this, but basically you can decompose this observation into three things. Okay, you can say this is the average treatment effect. So this is just based on the you take at the outcomes of the two groups, plus this is called selection bias. So this is a counterfactual. Okay, you get to observe this. This is someone who didn't move to an institution, and the citation in 10 years of that person. But however, this is a person who did not move to an institution, and the citations in 10 years. And this is a person who did move, and the citations if this person had not moved. So we cannot observe this. So this is like, how does the selection of someone, how does the treatment affect potentially the outcome? So that's the selection bias. Okay, so and then we have another factor, that's heterogeneous treatment effect bias. Okay, and this is is there a difference between the average treatment of the treated and the average treatment of the untreated? So selection bias, in the case of a medical example, a difference between groups, if both receive chemotherapy, what if they never receive a treatment in the first place? Heterogeneous treatment effect bias, difference between the surgery and chemo groups, counterfactually weighted by how many people went to chemo. And again, here you have counterfactuals. So heterogeneous treatment effect, we assume that the treatment effects are the same for all of the units. So this is usually an assumption that we make, so that we make this go away. So we make this 0. Yeah, and this is relatively reasonable in that we try to like the effect wouldn't change depending on the population of both cases. But this is really hard to get rid of. Like, what is like this counterfactual is sometimes hard to get rid of. So the whole idea of causal inference and the whole field of causal inference is try to get rid of this selection bias. Okay, So now, if we eliminate both this, which we are making an assumption that this is 0, and we eliminate selection bias, the average treatment effect will be equal to our simple difference in outcomes from the data. Okay, so we can estimate the causal effect, which is the ATE here, is what we're interested in, only based on the observations. Okay, so how do we do this? How do we do this elimination? There are many methods, and we'll go through just one in this class. Any questions so far? All right. So the simplest approach to do this, we assume that there is a conditional independence between the assignments. So if we choose the assignment, then there is the outcome. There is no relationship. The outcomes of the treatment and control are independent of each other. So this means in case of medical treatment, the reasons that we assign someone to a surgery are completely unrelated to what we think is going to be the outcome of the surgery. Okay, this is probably not true. In a lot of times, doctors select someone to go to surgery because maybe they think they're trying to predict how well someone's going to do. Almost all observations of human behavior violate these assumptions. Humans choose a treatment because they expect some gains. So, so let's say if the doctor selects a surgery independent of expected gains, it does some randomization. That would be one way of solving this. Sometimes there is a source of external randomness for assignment. So maybe, I guess, on Monday, this is just a teaser. I think on Monday, I hope Aaron or Dan present the results, and they use some of this source of randomness in their estimation. There are a couple of papers in Science of Science that use the randomness from scores in, let's say, grants. So in NIH, the National Institute of Health, there is a threshold. So if you pass a threshold, you get a grant. If you don't get a grant. And yeah, go ahead. Yes, you have a question.
Yeah, I would like to ask you a question. Usually when we are going to do these things, if we are going to model this, we are going to just generate some random numbers. We say, okay, we are going to generate some random numbers between 0 and 1, and then we have a probability. And if the probability at the number that we just get is less than that probability, we are going to say set it to 0 or 1, or and the otherwise. So I would like to say that in order to check that is this, it's not really, it is independent to whether we have, should we just have these random number generations and say, okay, we just did the random numbers based on these conditions, and the results are, not different to what it is in the usual world. Means that we are going to say, okay, these random numbers are different from those D that we have. Is that true? Do we have something like this here?
Not really, unless you're talking about the data that we already have. So if the data that we have, there was a random process, like someone generated a random number to assign units to treatment and control, then yes, you can use that. But after you have the observations, doing randomness in that assignment won't help you because you don't know the causal structure of your data. So you're kind of doing something that won't really remove the causal relationship in the data. So so imagine, I think it's good to think about medical trials, let's say for the COVID-19 vaccine. they randomize who, they gave the real vaccine to some people, not the real vaccine to other people. So having observation data of people who got the vaccine and didn't get the vaccine, not based on randomness, but then adding randomness after that won't really help, because the data that we have already comes from something that doesn't have randomness.
Mm-hmm. Yeah, perfect. Thank you. So sometimes B is really just related to the data in the causation, relation. Is that right?
Yeah, it's the data that you have already, well, most of the time it's data that you will already have.
Mm-hmm. Perfect. Thanks.
You're welcome. So if we assume some external sum of randomness, so I was explaining the idea of, let's say, an NIH, you get the threshold. So if you pass the threshold, you get the grant. If you don't get the grant. So you can think about that as a source of randomness, because having a grant that is 10 points versus having a grant that is 10.1 points, there's not a lot of difference. So you can think that there is a little randomness in the process of where you go up below or above the threshold. So you can take that as a source to assume that there is some independence, and you can assume this, and there is no selection bias. And also there is no heterogeneity treatment bias. Now, we usually need to make other assumptions that are more perhaps philosophical, that all units receive the same treatment dosage, like they will be, let's say if someone gets chemotherapy, they will be, the same, they will receive the same benefit as another unit, like another person. But that's not true, because doctors are better than others, and maybe you need to control for the doctor as well. There are no externalities. That's another assumption, and this is easily violated in networks and in epidemiology, as we have suffered through COVID-19. Some people, they choose to not take vaccines, so that affects other people. So whatever that other person is doing, it's really hard to estimate the effect of the vaccine of that person, because there are other people that are affecting, there are externalities that are affecting the outcome of that person. And of course, this is applies to all of machine learning. Like there is the observations that we get in our data are generalizable to the actual world. All right, so how do we think about this? Like how can we apply this very simple approach to our models or our data? So I'm going to introduce a concept called directed acyclical graphs. And this is a graph, and it's a network, but this is not related to what Stephen was talking on Wednesday, but it's the same language, right? So we have nodes, we have edges and things like that, but they mean something different. So the idea of DAGs is for you to lay out what you think the causal relationships are in your data. And this is typically a philosophical process, in the sense that, or an assumption process. You say, based on your experience, this is how you think the world works, and you make that explicit with a DAG. You make, this is how I think things are related. And the idea is that once you make the assumptions about how the world works, once you get observations of some of the variables that are in your DAG, you can make causal claims of those observations if you control for some of the factors that you assume might be at play in the data. And we'll hopefully give some examples of that. And the way that you make that connection, the way that you use the DAG with observational data, is that you want to block flows of information from your DAG that are external factors. You want to block those flows so that the observations that you have are not affected by unwanted confounding factors. Okay. So this will be a causal a DAG, but it's a causal graph. It's not a probabilistic one. So they represent relationships between variables. So we have 3 random variables. These are all like probabilistically random variables. But the arrows here mean cause and effect. So an arrow from D to Y means D is causing Y. An arrow from X to D means X is causing D, and there is another arrow to Y. This also means that X is causing Y. Okay, so we say that there is a path between the assignment. So D will be the assignment, and this will be the outcome. The assignment and the outcome. So we say there is a causal effect, but we also say that there is a backdoor path from D to Y. So you can go here backwards, and then there is another factor. So we call X, this is a backward path, we call X a confounder, because it can change the value of Y and D simultaneously. So if we have data on D and Y and X, we should be careful about X. Okay, so we cannot leave this open. We cannot just take the average of what happens to Y for different D, because X is affecting this. Okay, so leaving a backdoor open creates biases. And I didn't credit the author of this properly, but this is Julia Perel. Very, very vocal on Twitter all the time. It's very fun to read his tweets. So he's a researcher at UCLA, and he introduced this idea. Now this is the same as the other framework, but you can see it graphically. Okay, so it's the same. So sometimes we have variables that we cannot observe. So and that will leave us with all kinds of problems. So we need to make assumptions and discuss those assumptions, and that's why DAGs are so useful, because we can say, okay, these are my assumptions, but then someone can say, oh, you have this unobserved confounding factor and you're not controlling for that. Sometimes we have this effect. So this is also a backdoor path, but because we have this, we have a variable that is a collider. It doesn't allow the flow from D to Y because of the form of the arrow. So if the arrow goes like this, we call this a collider. Now, when we say that the backdoor is closed. So, so here's a little different, like in the sense that if you're familiar with graphical models from probabilistic inference, the way that we condition in graphical models is different from how we condition on DAGs. So if we want to close an open backdoor, so let's say I'm going to go back. Sorry about this. We want to close this. Okay, we need to condition on this X, so that doesn't affect the variables that we are interested in, and that will close the backdoor, so there won't be a flow of data. So if the backdoor is closed, we leave it alone. Okay, so we have this case, we leave the backdoor like this. So we leave it because there won't be flow of information. We can estimate the causal effect between D and Y. However, if we condition on that variable, it will open the door. Okay, so if I say, okay, I'm going to compute the effect of Y, and I will condition on X, that will be a problem, because it will open the door for having an influence between X and Y and X and D. So this is it's a little subtle to say to see sometimes, and I guess if I have time, I'll go through an example. Okay, so this is our previous example, and this is how we represent this with DAGs. Okay, so we say here X is directly related to Y, X is being caused by Y, and this is the last example. X is not causing Y because there is another variable that is causing both. And you can see that if you change the values, if you set X, it will change Y. Here, if you change X, it won't change Y. And here, if you change X, it doesn't change. It doesn't change Y because there is no causal relationship. Okay, so I'm going to show you like a very simple way of doing causal inference with observational data. People have used this in science of science papers, I believe. Maybe I'm wrong. Aaron and Dan have used this. So every time you see something like matching or subclassification, matching is like a more sophisticated form of subclassification. Now, the basic idea of this is that you want to assume that there is a variable that we can observe, an independent variable, that if we condition on that, the treatment becomes independent of the potential outcomes. Okay, and that satisfies the backdoor criterion. So we have a backdoor, and that we think it is affecting our ability to infer the causal effects. We can partition the data into different strata, different cells, and then compute independently for each of the cells the effect, and that will give us an estimation of the causal effect. Now, a typical example of that is, let's say, unfortunately, so Stephen talked about a paper that on Wednesday that was retracted, and I mentioned that paper in my, and this is again shameless plug about my paper. It's not even a paper; it's a preprint, so I guess not so shameless. Here. Can I do this? So I propose this effect. So they were estimating whether there is an effect between female mentor and impact. Okay, so we say there could be a causal effect, but I propose like an alternative diagram that is more complicated, where there is no effect between the number of female mentors and the impact, or woman mentor and impact, but rather there is a more complicated causal relationship when the popularity of someone, because let's say men have some characteristics that usually they kind of like to maybe boast a little more or advertise themselves more. So that will affect the popularity. So the impact could be related to popularity. And this is just an assumption. Okay, so I'm just laid out what my assumptions are. So if you don't assume any of this, if you don't control for any of these factors, popularity, the training that someone had, and the funding, then you might be having problems with your estimation. Okay, this was the paper, what they proposed. So they were controlling for all these factors because they were assuming that these are the factors that you need to subclassify. So they will take these subgroups, so people that have proteges, that are big shots, the number of mentors that they have, the gender of the mentee, the discipline. So they control for all of these things. That was the subclassification. And then within each of those cells, they look at the differences if you change the number of female mentors with the impact. Okay, but I argue, and others have done this, that there might be other factors that were not controlled, and therefore you could claim. popularity and affiliation. Yes, unfortunately, no. That's a good question, Eric. So that's the question, that can the arrows go both ways? Usually you don't have cycles, and if you have arrows in both ways, you will have cycles. Exactly. So I just said, now sometimes you can have time, so you can say, okay, if let's say popularity at time 1 is high, that can affect the affiliation, and type 2, and then time 2 affiliation can affect popularity at time 3. So you could do that time series of, and that's how it usually works in the world. And then you remove the cycle, but then it becomes more complicated. All right. Now, there are tons of ways of doing causal inference. I was saying, here's a sample of ways of doing it. So regression, I think that Schum's paper on whether getting a grant rejected helps you or not, or something like that, uses the regression discontinuity or difference in difference. The regression discontinuity. Difference in difference, I'm not sure. CM is what the paper that I showed you before, that's what they use. So these are just the different techniques they have. It's very it's relatively new in the sense that only now people in machine learning are paying attention to this and trying to scale them. So these methods are relatively old, but they used to work with relatively small data sets. So but now we have people are getting more used to it, to them. Okay, any question? All right, so I have a little demo that is kind of silly, but I think it's interesting to see just how the math works and how you can run things with code. So I assume most of you are familiar with the Titanic tragedy, and I'm interested in understanding the effect of being what is it? The effect of being in first class versus not being in first class with your probability of survival, whether you survive or not. Okay. So the first thing is I'm going to establish a causal model. This is an assumption that I make. You might not agree with the assumption, and we can debate that. But if you agree, we say, okay, that sounds fine. Then I can do the math and estimate the causal effect. So I'm going to make the following assumption. Yes, there is a causal effect between the first class or not first class and the survival in this tragedy. However, there are other confounding factors, and you probably might agree with this. If you were a woman at the time, usually for reasons that I won't get, and this is an assumption, you might go into, that might affect your ability to go to first class, right? So the woman, the gender affect whether you go to first class or not. Also, if you're a woman at the time, usually people will defer to, they will say, okay, woman first. So you will go into the boats and get rescued, more like you will be more likely to be rescued. So that also affects the survival. Okay, so these are confounding factors here. The same thing with children. Okay, the children, say the children usually were in first class because third class, they were traveling. Not even, I don't think it was even for pleasure. I'm just making stuff up here, but there could be an effect between children and the class, and children being rescued because people will say, okay, children and women first, let's put them on boats and save them, and then men will defer to them. That could also affect the outcome. Question? Yes.
Yeah, actually, my question is that how we could infer this causal model means that, okay, we know that if somebody is a woman or not, or maybe we can have the age of that person, we can find out is that a child or no, and we know that if someone is in the first class or not, maybe we have eight or nine more columns in our data, and we just look at it. So how we can say, okay, this is the causal model that we just found for these things, and okay, with which probability is the right causal model? Means that if we have a lot of causal models, which one is the best?
Yeah, that's a great question. That's a question that everybody wants the answer to, and I don't think we have an answer. And I believe it's not possible. Like, this is like, I don't think you can answer that question within the system itself. You need like data outside the system. So you need data outside the observations that you have, in the sense of like data about tragedies in general, data about like metadata about this process. So in a sense, it's impossible, I think. I'm sure people have tried to do this, but I think it gets more into the philosophical, because within the system you cannot answer that question. But yeah, that would be great. Now, I don't know if you can compare. Yeah, I don't know if you can compare causal models.
Oh, yeah.
Oh, sorry. Go ahead.
Sorry. Internet connection problems. Sorry.
Oh,
please go on.
Yeah. So, unfortunately, I'm not aware of ways of doing that. Okay, so I will load the data, the Titanic data, and here's the data. So we have the whether someone survived or not, and whether we're first class or not. So I just codify that. Now, if I look at just the DAM average, so I take the average of the class and the survival, yes, we see an increase, right, from 0.3 to 0.5. So the average difference in observation, the dummy way of doing it would be, 0.2, 0.25 difference, right? Oh, actually, well, let's see, 0.35. I was not even close. So what I will do subclassification. So I will say, okay, I'm going to take the people that are in this. I'm going to partition, I'm going to control for this, because these are open backdoors. I can have a cycle that goes backdoors here, the back with this cycle. So I will take pieces of the data where the gender is the same and whether it's children or not children is the same. So I will have these cells. So basically, these 4 possible combinations, and then I will compute the differences between these 2 things. And the math is a little bit more complicated than that, and it's here. And that will give us that the causal effect, instead of being 0.35, is really a little lower. And by a little lower, it's like half of the effect. It's 0.18. Okay. So with this, again, you need to assume something about the data, and something about the causal structure, and then you can make these conclusions. Now, the cool thing is that you can say, okay, the causal relationship between being first class and survival or not surviving is this. Okay, so it's not an observation example. Any questions? Now, I will say that subclassification is generally something that we don't use these days because it's too strict. We need to have exactly the same values. So in this case, we could, because we have binary variables. We have woman, not woman, children, not children, but usually you have continuous